So our next session, it is my pleasure to introduce Tim DiLauro, who is digital library architect at the Sheridan Libraries at Johns Hopkins University, and also wears another hat as technical director of a new effort called RMAP, which is an effort, combined effort of three organizations to build out this mapping that, again, Christine had mentioned about the network of an article, mapping the original idea of the article and the data surrounding that. And so, without further ado, Tim, please welcome Tim DiLauro.
Thank you, Jerry, and thank you, Ivka, for the invitation to present to you. I'm going to introduce you to the RMAP project, give you a very whirlwind kind of tour through the technical capabilities of it, and at the end, suggest some ways that you can help and hopefully incentivize that through some ways that we can help you if you provide some help to us. So, scratching backs. So, how did we get started in this? 5 or 6 years ago, we were doing some projects looking at submission of articles and how we might help authors get their data in and create linkages between data in their articles, in their individual articles, and their figures and tables, and the data sets associated with the content in those articles. And we realized that this is the new mode, and I think we've seen enough of it today, just today. It's very clear that the new scholarly object is a graph of things. It's not the traditional article. And in many circumstances, the traditional article is not the object of long-term interest. That the article might be of interest at the beginning. It might be of interest for tenure and promotion, but the data or the software that is associated with an article is sometimes even more interesting to a broader set of people. It's also important to note that these data are these entities are distributed. They're not vested with the publishers necessarily. The articles might be, but data sets, software, preprints are often in other places, so we need ways to connect these pieces together. And in order to understand these objects in the long term, we need to understand their context. So our group got together sometimes a little bit by accident, by just, I think Jerry saw Saeed talking about this at a meeting, and we knew the work that Portico was doing, and so we were able to get together by just sort of finding each other in the wild. So we have the Data Conservancy, which is where I'm from, which is based at Johns Hopkins, IEEE, which has expertise in journal publishing and in society publishing, and Portico, which has expertise in archiving of these and preserving for the long term the traditional publication. And I should have mentioned that we have generous funding from the Alfred P. Sloan Foundation. It's always important to thank your publishers, or your funders. Some of our high-level goals as we started to put this project together were to have a tool that actually worked and did something, hopefully something that we could use or adopt, but also something that we could potentially offer to the community at the end of the project. We wanted to have partnerships with the community, which is why I'm here, and we wanted to be able to support these new kinds of scholarship that are going to be enabled by hooking these resources that are spread out back together. And of course, in order to actually deliver a service based on this technology, we wanted to have some different models, pull together some different models for sustainability that would enable that. This is our work plan. We're a 2-year project. We are in the 2nd year now. We've gone through an initial requirements gathering phase. We've had a workshop, talked to some stakeholders, and refined some of our goals based on those conversations with the workshop participants and others that have communicated with us. And we've actually developed a prototype a little bit ahead of schedule. It's very minimalist right now. We are in the 2nd year, and we're going to take that prototype further as we go along. So this is the whirlwind part. It's probably going to seem to go extremely fast, but hopefully this will give you a sense of what the technology is, how it works, the models that are supported in it. So our key objectives from the technical perspective were to be able, and this is actually, this first one is beyond the technical perspective. It's from the perspective of the entire project, is being able to support assertions, linking from a variety of possible participants in the scholarly value chain. So not just the ones that are the ones that I think a lot of people in this room think of primarily, so services like Crossref. People who are participating in Crossref, I think, are very much on your radar already. But there are institutional repositories, there are software repositories, there are other kinds of artifacts that are not currently included that could add valuable context. Integrating with linked data, I think linked data is our future. I think we've seen enough here this morning that for me to know that many of you acknowledge that linked data is the way that we're going to go forward, and it gives us an opportunity to make connections in less rigid ways. And the last thing I wanted to say here is that we talk about a lot of these resources that have identifiers, but I think we know that a lot of the content that we have has entities that don't have identifiers on them. For example, authors on many papers are just listed as an author without an ORCID or a researcher ID or things like that. We also have textual citations that don't have an associated identifier, and we want a way to accommodate that in our model as well. So this is a very simplified version of our data model. I'll walk through it very quickly. So in our model, we have the concept of a resource. It's similar to the concept of a resource in the web. The little green highlighting on the back there will hopefully help you find it here in the graph. And I don't think I need to say much more about that, except that it's a key component in the RMAP model, because many of the other things in the model are resources, and resources will be the target of interest when you're trying to find something in our graph and want to find more information or context about it. An agent is someone who is, or a person or a thing, who's responsible for performing some action. That action could be in the scholarly realm, and we treat that separately. That's a scholarly agent. Or it could be someone or an agent who's doing something in the RMAP system itself, and we call that a system agent. We currently make a distinction between those, but over time, hopefully, there will be some overlap between those system and scholarly agents. Events are very important because we want to support a record of what has happened within the RMAP system or within an instance of RMAP. And so RMAPs record things that are performed by a system agent. And if you want to have information, provenance data that is coming into the system, that can come in as a regular resource. RDF triples are the language of the semantic web, basically analogous to subject, verb, object in the English language. And finally, the disco, and this is a very key component in our architecture. This is actually the distributed compound object that will be the primary form of communication between people who are creating objects and registering them with RMAP. So this is the primary unit of registration within RMAP. A disco looks like this. It's very similar to the OAI object reuse and exchange model, where you have a compound object, and that's represented here in blue, in the blue dashed line, and things that it connects to out in the broader world, and those are inside the red disco. The disco contains the entire part. And now I'm going to walk through, over on the right-hand side, you'll see an incoming disco. On the left, the RMAP linked data graph. And over time, as objects come in, a data set is created. In this case, there's a contributor or a creator, and that data set, D1. Now some software is being registered. It happens to be coming from a software repository, and now the graph consists of these things. And so I'll walk through this. From that software, data set D2 is generated using D1 as input. An article is written that has some, it's related to D2. There's some discussion of D2. So now this graph has the article and the relationships between them. And you can see the gray outline here is just showing you the area of interest on the graph for this incoming disco. Someone else comes along, another creator comes along and creates a new piece of software, and that gets registered as a push from the software repository. Another data set, D3, is generated from that. And that same agent, a person, writes an article about that. And now you can see that there's a lot more in this graph, and you can imagine over time that there will be many, many more interconnections, and there's really a lot of context to see here. Let's see, in this last one, the identifier was entered as A2 as an example, and in this next one, the contribution is corrected. The identifier should have been A3, and the active view of the graph is changed, although the history will still be there. So A2 is not an active, the disco that was associated with that is no longer active, but it is still available in the RMAP system. So now we can ask interesting questions like, well, what are the things that are related to D1? And so I've grayed out the other parts of the graph, and you can see what is connected. These are first-degree connections and the relationships between all of them, and you can see the graph there. Here's another example with Creator 1. And you could imagine that a service like ORCID could go out and query RMAP with Creator 1 and find out what resources are associated with that and gather them up and expose them through that creator's ORCID profile. And there's what Creator 2's looks like. We're using RESTful APIs, and I'm going to go through this very quickly. For a variety of reasons, programming language independent, and easy to test with tools that are available on people's desktops already. These are in the slides just so you can look at them later. And these are the things that we try to capture about our APIs: behaviors, the RESTful paths, the data models for the interactions, and the serializations of those data models. And we have implementations for those as well. And this is what that looks like, this simplified version. Our API coverage is currently focused on getting stuff in. In the future, we're going to be looking at authentication, administration, like user management, composition and normalization, so making the graphs look similar, inferencing, where a concept encompasses another concept, and so you can find information that's broader than what you actually searched, and system operability, like understanding what's in the system, how much stuff is in the system. Another thing that we want to be able to support is harvesting, so that if a participant in the ecosystem is not able to code directly to the RMAP instance, if they have capabilities like OAI PMH or resource sync, other things like that, that we could actually harvest their data. And we're also using that to populate things like DataSite. So community engagement, we got some feedback from, this is some of the key feedback from our workshop participants. I'm not going to say too much about that so that I can get to the main message since I'm a little bit over time. So what can you do for RMAP? We would really like to have your help. We would like to get feedback from this community about the way we've done things, the things that we think we'd like to do, and see how they align with your interests. We'd like to use your data in some cases. So we need to get data of a wide variety so that we can understand how well the system works with different kinds of things. So journals, repositories, funders, creators, project information, data software, instruments, and samples. And we'd like you to consider using RMAP when we are publicly releasing those capabilities. And these are some of the things that we think RMAP can do for you. Reduce the cost and complexity of transforming information from multiple systems. Reduce the cost and complexity of normalizing data. Reduce the cost and complexity of developing interfaces between systems, and streamlining the logic for deciding which objects are of interest to you. Team members and more information. Thank you very much.